Okay, now we see an important theorem on subgroups. This is called the Lagrange's theorem. It says if a group H, okay, capital H of order small h, order is the number of elements in the group. If it is a subgroup of a big group G of order small g, then small g, the order of the big group, that is actually an integral multiple of small h. That is g is equal to, small g is equal to n times h, where n is what? An integral number, 1, 2, 3, etc. Okay, so order of a group is always equal to integral number of times the order of the subgroup. Okay. Now, suppose that H, capital H is, we are going to actually prove this theorem. So the capital H, the subgroup is consisting of elements E, H2, H3, HH. Okay. Then what we do is we form the left coset of this subgroup with respect to X. Okay, with respect to an element X which belongs to G but which does not belong to H. Okay, so we are taking an element from a group G which does not belong to H. So if you take, if the element is taken from H, we will be simply getting H, just a rearrangement of elements. So what we are doing is we are taking an element from group G which does not belong to H. Now all the elements XH, all the elements XH belong to G, but none of them is a member of H. This we have proved earlier. All the elements that we are getting XH that belong to G, but none of them is a member of H. Okay, thus we have small h new elements of the group G. Okay, we have small h new elements of the group G. Okay, so if we take H union XH, H is the subgroup, XH is the subgroup, the coset formed by multiplying H with the X. X is an element taken from group G which is not a member of the subgroup. So if you take H union XH, you will get two H elements, two small h elements, E, H2, H3, HH, X, XH2, XHH. That way we will get 2H number of elements. Okay. Now if this does not exhaust the group, what that means is group G still contains some more elements. Then what we do is we pick up an element from the remaining elements of G, okay, remaining elements of G, such that Y that we are taking does not belong to H nor it belongs to XH. Okay. So we are choosing Y in such a way that it does not belong to H or XH. Okay, the coset we formed earlier, XH. So we are getting new elements, YH elements, Y into H. Okay, Y into H is the left coset of H with respect to Y. Okay, so we will be getting small h number of elements. We are forming left coset of H with respect to Y. Now the elements that we are getting in YH, it must belong to G. The elements YH that must belong to G, but no element of YH belongs to H. That we have seen. And when we took XH, there we said XH, no element of XH belong to H. Same way here we say no element of YH belongs to H. That means H and YH are disjoint. That is H intersection YH is null set. Okay. Next step is we prove that the sets YH and XH are disjoint. Okay, we now prove that the sets YH and XH are disjoint. That means none of the elements in YH belong to XH. That is XH intersection YH is a null set. Okay, so this we have to prove. So for proving this, what we do is, suppose that an element of YH is identical to XH, an element in XH. So we start from a contrary hypothesis. Okay, suppose that one element of YH is identical to an element in XH. So YHI is equal to what? YHI is equal to XHJ. Okay, and Y now if I multiply, post multiply it with HI inverse, I will get Y on the left hand side and XHJ HI inverse on the right hand side. HJ HI inverse, HJ HI inverse, that is HK. So Y is equal to now XHK. This is definitely, this XHK is definitely an element in the XH, which shows Y belongs to XH. Okay, so but we know we have taken Y from G such that it does not belong to XH. Okay, we have actually chosen Y in such a way that it does not belong to XH. Okay, so if we started from this assumption that YHI, one element of YH is identical to XH, that is YHI equal to XHJ, what we are seeing is that Y is an element, or Y belongs to XH. That is, contrary to the hypothesis. Okay, we have chosen Y in such a way that it does not belong to XH. So what we are getting is, when we take YH, we will be getting small h new elements of G. Okay, we will be getting small h new elements of G. So totally we have 3 small h new elements. Okay, we have 3h elements. So first we started with the subgroup H, then for XH we got h small h new elements, and then for YH we are getting again h small h new elements. So totally there will be 3h new elements. Okay, so H union XH union YH. Okay, H union XH union YH, that will now contain 3H elements, 3 small h elements. Okay, now if this still does not exhaust the group, then what we do is we pick up. Okay, if this does not exhaust the group G, then we pick up one of the remaining elements of G. Okay, as we did in the case of XH or YH, we pick up one of the remaining elements of G that does not belong to XH, that does not belong to H, XH or YH. Okay, so we will be getting H new elements. So this process can be continued until we exhaust the whole group G. Okay, so each time when we form the coset, left coset, we will be getting small h new elements of the group G. Okay, so that means the order of the group, first we had a small h elements in the subgroup, then when we formed the left coset and the left coset XH with H have 2H elements, then we took Y and again formed the left coset with H. So H union XH union YH now have 3H elements, and we continue this process. So each time we will be getting small h new elements from group G. Okay, so this process is continued. So that will be always adding small h new elements each time, and we stop when the group is exhausted. Then the number of elements in the set that we are getting, actually we will be finally getting the group itself. Okay, when you continue this process, start with the subgroup, then union with xh, then union with yh. That way you continue this process and you will be finally getting back the group G itself. So starting from a subgroup of order H, through this process we are generating small h new elements each time. So and finally you are getting the group G itself, which has small g number of elements. So what can we say? The G, the small g, the order of the group, that is integral number of times. Here we have taken m, can be n, integral number of times the order of the subgroup, or the ratio. Okay, and the ratio g by h, that will be an integer. This is called the index of the subgroup h in G. Okay, this is called the index of the subgroup h in G. Okay, small g by h, that is called the index. Okay, g by h is actually this number m, integral multiple that number. So this is called the index of the subgroup h in G. Okay, so this is an important theorem with regard to group